Hi everybody, this is the third lesson in the Physics A-Level electricity topic. This is electrical power. So this is a relatively short set of ideas. We're going to just introduce electrical power, and we're going to also do the exam questions in this same video. So we're going to talk about the electrical power formula and the derivation of it, and look at a few worked examples, a few calculations, and then one exam question. Again, it's quite difficult to find a kind of grade A-star question on this. I found quite a tricky one, and I think that'll be useful to use. But as we mentioned previously, as we progress through the electricity topic, then the questions will inevitably start getting more difficult as we bring in more ideas together. So a context example, which I thought was quite nice, was the power output of the sun. Obviously the sun is enormous, we know that, but we forget how vast it is and how much power it is releasing per second. So the power output is 3.8 10 to the 26 watts. So that's 3.8 10 to the 26 joules per second. So if we think about the USA, so at the moment its electrical consumption per year is 1.44 10 to the 19 joules. So using power equals energy over time, which hopefully you've seen before from GCSE, we can make T the subject and divide the first number by the second number, and we can get this large number here, and it turns out to be 26.4 million years, which is unimaginable. So there's a vast amount of energy available from the sun. Obviously it's very difficult to harness this, but this is one of the interests in renewable energy, is this is an enormous amount of a limitless energy. So if we can tap into a tiny amount of it, we can power an enormous amount of devices. So let's have a look at the formula. So hopefully you've seen certainly this first one at GCSE. You may have seen these two here as well. So P is equal to V times I, and there are two other variations, I squared R and V squared over R, and we're going to derive those right now. So derivation, we mentioned this last lesson. This is the algebraic proof or illustration of where a formula comes from. So we know that this expression, mechanical power from GCSE, and possibly even Key Stage 3, power is energy over time, or work done divided by time. And if we know that work done or energy is V times Q from last lesson, then we can substitute W equals V times Q. And we know that Q over T is equal to I. So we get power is equal to V times I. So you may or may not need that for the exam. It's always useful to know where these expressions come from. We can do something similar once we have P equals VI. If I substitute V equals I times R, now we haven't looked at this expression in this series of videos, but you're probably very familiar with that from GCSE, V equals I times R. So we can substitute V equals I times R multiplied by I, and we get I squared R. And the third variation is substituting for I. So we make I the subject, I equals V divided by R. So V over R multiplied by V gives us V squared over R. So we have three expressions for power. Which one we use depends on the information we're given in the question. So for example, we might be giving this question here: what current flows if we have a 60 watt bulb and we're connected to 230 volts, which is probably mains. So we can make I the subject, I equals P over V, substitute the values, and we get 0.26 amps. Alternatively, question 2, if I'm given the power of 5 kilowatts, which is 5,000 watts, I'm given the resistance of 120 ohms, then that's resistance, power, and we're trying to find current. So it's going to be this expression here, P equals I squared R. And what we need to do is to make I the subject, so divide both sides by R, P over R, and then get rid of the squared to give us square root, substitute the values, and we get 6.45. I've picked three fairly similar questions here, fairly similar to the previous screen, for you to practice. So as we've done previously, pause the video, have a go at these on a piece of paper, and when you've answered them, press play and you can check your answers. Right, so this first one, we're given the power and we're given the current. We're trying to find the resistance. So we want power resistance and current. It's going to be this expression here. We're trying to find resistance, so make R the subject. R equals P divided by I squared, so we don't need to find the square root here. So 150 divided by 5 amps will give us 6 ohms. Or you can write the little horseshoe, the omega, rather than the word. Question 2, we're given the power 2 kilowatts and we're given the resistance of 150. So we're trying to find the current, so it's going to be, once again, this expression here. But now we're making I the subject, as we did in the previous slide. So divide both sides by the resistance to give us P over R, and then get rid of the squared, square root, 2000 divided by 150, and we get 3.65 amps. Question 3, a little bit more tricky. There's 2 stages to this. It says find the energy in megajoules. Okay, we've got the voltage is 230, resistance of 200 ohms, and a time of 12 hours. So, first of all, we need to find the power. Well, we're given the voltage and the resistance. So it's going to be this expression here, P equals V squared over R. So we've got V squared, 230 squared divided by 200, which will give us 264.5 watts. And the final stage, we're trying to find the total energy, and we know the time. So E equals P times T, so we've got our previous value of power multiplied by 12 hours. We need that in seconds. 12 times 60, which will give us this value here, which is quite large. And it wants it in megajoules. So there is a button, hopefully on your calculator, depending on your calculator, which might have the letters ENG. So quite a useful little tip here is if you press that, that'll put it in either a kilo, mega or giga, or going the other way, milli, micro or nano. So if you want mega, which is 10 to the 6, then you can press that a couple of times and it should put it in the correct format for you. So the previous slide, the questions were pretty straightforward. This is an exam question. As we mentioned previously, it's quite difficult to find a question just on power, which doesn't draw in lots of other ideas. So this one seems quite good. So have a read through the question, pause the video, and once you've answered as much as you can, press play and you can have a look at the solutions. Right, so part A. So quite a typical question. You're presented with a relatively or seemingly simple circuit, and we're presented with an issue which used to happen a lot with old-fashioned filament bulbs, that the bulb would blow, so the filament melts, and that changes the nature of the circuit. So first of all, what actually happens? Okay, well, we'll state what happens and then we'll explain why. So we said that the filament in lamp B melts, so that's effectively removed from the circuit. What would happen is that A would become brighter and C will become dimmer. Right, so we need to explain what's going on here. So, first of all, we need to understand about the resistance of this parallel section. Now, we will look at resistance of series and parallel later on in this series of videos, but we should be able to understand this reasonably intuitively at this stage. So, we know that if both of these lamps are working, then the current will split. So, some will go this way and some will go this way. And one of the characteristics of a parallel circuit is that every extra loop you add, the resistance goes down because of this splitting of the current. So if you effectively remove the bottom loop because the filament in lamp B is melted, then you've got a greater resistance. This is quite a counterintuitive idea. But if we can accept that, if the resistance of this parallel section, what used to be parallel, has increased, then that is now going to take a larger share of the supply voltage. So the brightness of A will increase. But the total voltage needs to be the same. So if this section here, or lamp A, is taking a larger share of the voltage, then lamp C must be taking a smaller share of the voltage, so it will become dimmer. Okay, so that's quite a difficult question. That's not intuitive at all, but it's drawing together ideas of energy, of Kirchhoff's first law, of voltage in series and parallel. So some very important ideas there. Part B should be a little bit more straightforward, hopefully. We're told the power rating, so 60 watts and 5 watts, so the same voltage, but different power ratings. We need to work out the electrical energy used over 8 hours for 20 days. So we could think about the two, well, any expressions we might want to use. But we're not actually told. We are told the power and we're told the voltage. We're not told the current. We don't actually need to know the current, so that first expression is not required. What we do need to know is E equals P times T, and that's it. So we don't actually need to know the voltage here. So just E equals P times T. So for the first one, lamp P, E equals P times T, I have 60 watts multiplied by the time, so that's going to be 8 hours. So times 60 times 60, that's the number of seconds in an hour for 20 days. And we get this number here, so it's quite a big number, 3.46 times 10 to the 7 joules. Quite a useful thing to be aware that the joule, 1 joule, is quite a small unit. So if we have even just a relatively low power bulb that's staying on for a number of hours, we get really, really big numbers. So, and obviously we need to use standard form. So part Q, or rather for lamp Q, same calculation. The only difference is the power rating has dropped to 5, so we're going to get a slightly smaller value. It's still quite big, but it should be 12 times smaller. 5 times 12 is 60. So we've calculated the total energy used in each of these lamps. Suggest why the two lamps can have different power ratings but the same light intensity output. Okay, so what have we got for this one? We need to talk about how much energy is wasted. We could refer to the efficiency. If we mention the power rating, we're probably not going to get a mark because it's referred to power ratings here already, and it's hopefully clear that lamp Q has got a lower power rating. So we can see mathematically that the lower power rating gives us total energy which is smaller. The same light put intensity. So basically they're having the same voltage, but we've got less energy wasted in lamp Q. So we could refer to as efficiency. So, but again, I think it doesn't say that in the question. I think if we just refer to energy efficiency, we might not get the marks. So we need to talk about filament lamps being less energy efficient because more energy is converted into heat. But in bulb Q, less energy is converted into heat than in P. So a little bit of a fiddly question, possibly a bit tricky to get 2 marks, but we need to talk about how much energy is wasted and how that relates to their power ratings. Right, good, well done. So that is electrical power. I've not included a review of this particular video because there's only really these 3 formula, and we've used those several times. I haven't created a Kahoot quiz for this one. Okay, that's the end of the video.